lecture in dynamics. On lecture number 2, we covered sections 11.1 and 11.2. Then we're going to skip 11.3 because it's optional. It has to do with graphical solutions, and it's very interesting, but with modern computing power, it's sort of a premium on the amount of time we can spend on the topics in here. 11.3 is sort of less necessary in terms of solution technique. And then we're going to talk a little bit about section 11.4. But what I'd like to do today, because on this last lecture, I had lectured for an entire hour and had never gotten to do any problems. So I want to do a few problems that are either from your homework set or very much like the problems from your homework set. So today, if you take a look at our Moodle page, you'll see that the first thing is, I wanted to show you a couple of little changes because I work with this page all the time. So we have our introductory lecture, which, since it has this little symbol, means that the lecture is posted and available to you. Then I have done lecture number 2. Now, the download keys here just mean I haven't got the lectures recorded yet. So I'm recording lecture 3 today. But what I've done is, where I have the submit button, remember submit for success, to turn your homework in, I've started to write the homework sets. So the first homework set, which would be from lecture number 2, are these problems. And then the second set is fewer problems. That'll be from the little bit of lecture that I do today. Now, the reason for that is just because sections 11.1 through 11.4 are very foundational, and there's just a bunch of stuff that we have covered. So there's less particulars in today's lecture, but generally speaking, this is a rule of thumb. This is not a for sure thing, but every chapter I will cover in approximately 3 to 4 lectures, and you'll have about, for the entire chapter, about 15 to 20 homework problems. So that's what I'm kind of aiming at. So that's kind of the way it is. And I do tailor them. If the homework problems are terribly involved, you'll have fewer of them, because obviously they're going to take a lot longer. So that is where we're going today. So today in class, I would like to work out problems 11.5, 11.3, 11.48, and then 11.9 is actually from section 11.4. So I'll work out these 3 problems, 5, 33, and 48, so that you'll have a record of those. Oh, you can't see it yet. And then I will, lecture a little bit on section 11.4, which is going to be very brief. And then, if we have time, we'll do the problem from section 11.4. All right. So the first thing we want to do is to take a look at problem 11.5 in your textbook. And I will just read it to you, and then I will go through the steps of the solution. So 11.5 reads, the motion of a particle is defined by this relationship. X is equal to 6t to the 4th minus 2t to the 3rd minus 12t squared plus 3t plus 3, where x and t are expressed in meters and seconds, respectively. Determine the time, the position, and the velocity when acceleration equals 0. All right. So we need to bring in these ideas that we came up with in the last lecture, in lecture number 2, that tells me that if x is a function of t, that dx dt is equal to v, and that dv dt, or the second derivative of x with respect to time, is equal to the acceleration. So what I'm really looking for when I have a mathematical relationship like that, and it says when acceleration is equal to 0, I'm really looking for when the second derivative of that function with respect to time is equal to 0. All right, so let's go ahead and just do our derivatives first. My velocity then, which is dx dt, is going to be 6 times 4, 24t to the third, minus 6t squared, just a polynomial, kind of nice, plus 3, and of course the constant term goes to nothing. So my acceleration is then going to be the derivative of velocity with respect to time, which is 3 times 24, which is 72 t squared. Sorry, what did I do?
The third one.
12 times 2, yeah. 12 times 2 is 24. Thank you. You're absolutely right. And whenever I do that, I'm not doing it to be cute in any way. It's a total mistake. So please let me know. Thank you. So we have 72t squared minus 12t minus 24. All right. So this is my function for acceleration. I want to find out when that's equal to 0. Hang on just a second. I just want to make sure I wrote that down correctly. 6 times. This was t to the third, 6. Okay, yeah. I don't know why I looked like I hadn't copied that down properly, but it's okay. All right, so we want to find when acceleration is equal to 0. That means that 0 is going to equal 72t squared minus 12t minus 24. And this is going to be a quadratic equation, isn't it? And if you think about it, if t has a negative root, that doesn't really make any sense, does it? That means that happened before. So it's something that has to do with the function, not with the reality of when the acceleration is going to be equal to 0. But each of these will divide by 24, won't it? So I can simplify this equation just by dividing that by 24. So I had 0 is equal to 3t squared. Oh, wait, that's too much. Let's do 12. 6t squared minus t minus 2. Right? That just looks weird to me. I just feel like I've done something. So if I take a look at this, then if I want to set up a quadratic equation, I know that the solution is correct negative b plus or minus the square root of b squared minus 4ac all over 2a. And you can also break that down just looking at what the numbers are, but this is the way that it always works. So if you don't see the solution right away, we can just go with this. So we say negative b is equal to 1. So negative 1, negative 1 is positive 1, plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So my two roots to this equation then would be 1 plus or minus the square root. 1 squared is just 1. And it's negative 1, but negative 1 times negative 1 is still 1. Then I have a negative times a negative, so this is plus. 6 times 2 is 12. Times 4 is 48 over 12. 1 plus or minus the square root of 49, which is 7. So 1 plus or minus 7 over 12. So if I take the positive solution, I get 8 over 12 seconds. And if I take the negative solution, I get negative 6 over 12 seconds, which doesn't make any sense, right? That's just a trivial answer. So I get 8 over 12 seconds, which would be 2/3 of a second, is the time when acceleration is equal to 0. All right, so it asks me, what's the time? 2/3 second. What is my x? Well, I'd plug 2/3 back into this equation, right? So I'd get 6 times 2/3 quantity to the fourth minus 2 times 2/3 quantity to the third minus 12 is 2/3 quantity squared minus 3 times 2/3 plus 3. And I know that you are more than capable of solving for that number. The only thing remembering is that it's going to be in meters. We have to make sure to include our units. And then velocity, similarly, we would use this equation. It's going to be 24 times 2/3 to the third power minus 6 times 2/3 squared minus 24 times 2/3 plus 3. And that, once again, I know you can solve that, and the units will be in meters per second. Okay.
On the homework, does it matter if we just use a decimal?
I like decimals. Yeah, it just popped out to me that way. So, but yeah, you can use decimals, absolutely. Okay, so do you guys have any questions about that? All right. So let's take a look at number 33 and see what I liked about that problem. All right. 33 says we have an airplane, which I'm going to draw a very small airplane because I'm not very good at drawing airplanes. So it's kind of just a little thing like that with the tail. Got some tricycle gear. There we go. That's kind of what I think an airplane looks like. It kind of looks like a duck, doesn't it? But we'll call it an airplane for today. An airplane begins its takeoff run at A with a velocity of 0 and has a constant acceleration. The acceleration of the plane is a constant. Okay? It becomes airborne 30 seconds later at a distance of 900 meters. The distance AB is equal to 900 meters. And it asks, what is the acceleration, which we're told is a constant, and what is its velocity when it takes off? In other words, when it hits point B. All right. Well, what do we know? We know that at A, let's call the position equal to 0. And we know that the velocity at A is also equal to 0. So if the acceleration is constant, we know that dv dt is equal to acceleration, or is equal to some constant. So I can say then that dv dt, I could just divide that, a dt, and I know that the velocity, I don't know the velocity at point B, but I do know the velocity at point A, and this would be the time at point B and the time at point A. This then is going to be the velocity at B minus the velocity at A. Acceleration is constant, so it comes out of the integral sign, and this just becomes the integral of dt, or the antiderivative of dt. So it's tb minus ta. Further know that the velocity here at A is equal to 0, and I know that the time at A is equal to 0. It means that I can say that the velocity at B is equal to the acceleration times the time. Okay, well, I don't know the velocity at B. I do know the time, but I don't know the acceleration. I just know that it's a constant. So I can say then that dx dt is equal to v. Separate that equation. And if I differentiate, I can say between x at B and x at A, I know that this is going to be 900 meters minus 0 meters. Okay. And if I take a look at this, I know that my time here is 30 seconds. And I know that my time here is 0 seconds. All right. So I don't really know what this is because it is it's a function of time itself, right? We don't really know what that is. But we also know that that's going to be linearly increasing. Okay? So if we could just use this as a function and say v is equal to a dt. And we could put that in there. So we could just say that x sub b is equal to a times t, I'm sorry, that shouldn't be, times dt. And if I do that antiderivative, at x sub b, since I have t dt, I know that acceleration is constant. That means that this is t squared over 2, evaluated at 30 and 0. So I'm going to say x sub b then is equal to a, oh, I know what this value is. This is 900 acceleration times the time of 30 seconds squared over 2. So I can say 900 times 2 divided by 30 squared is equal to the acceleration. 30 squared is 900, so that's just 2 meters per second is equal to my acceleration. So I can then say that my velocity at b is equal to 2 times the time it takes it to get there. This is meters per second squared, excuse me. So I'm left with 2 times 30, or 60 meters per second. Okay. The acceleration, so my takeoff velocity is 60 meters per second, and the acceleration is 2 meters per second squared. Okay. All right, any questions? All right, the last problem that I want to work on this section is 48. Yeah, 48. And 48 is a pulley problem. And this is a little different than the one we constructed in class, but I really like this problem because you have to look at the problem to make a determination about what is constant here. Okay? So we have some sort of a motor, and we basically have a cable that is, ooh, this is too far over. I should put this right here. Okay, well, let's put our motor here so I don't have to make it look weirder than it is. So there we go. We have some point C that we're going to be evaluating. We have a motor that's either spooling out, spooling up, or letting down a cable. And this cable is connected to an elevator. Okay. Now the elevator is likewise, I'll have to give it a little extension over here, connected to another cable and another pulley that then has a counterweight hanging down. All right, now the interesting thing about this isn't anything. That was just me attempting to put my pulleys in before I put my weights in. The interesting thing about this is there's a relationship between these lengths, but it's not all one cable, is it? There are two different cables. So there's this cable, which I would just call little 1, and this cable, which I would call little 2. And basically, the length of little 2 is not going to change, right? So I can say the length of little 2 is a constant. And similarly, the cable that's being spooled out or in, little 1, is also a constant. Now the other thing is that this elevator is not allowed to tip. So in other words, the elevator is moving however the elevator is moving. We can't cut it in half and have half of it fly off into infinity. It has to all come together. So E, the elevator, is attached to cable little 1, and it's attached to cable little 2. So we actually have 3 geometric relationships going on here. So if we look at cable little 1, and point C is just some point. Maybe they put like a little red dot on the cable. But you can think of it just like anything else that would go up and down, like a weight or anything else. But what we can basically say is that if I take this length and add it to this length and add it to this length, that would be the length of little 1, and that has to be a constant. So wherever C is, I could say the y to point C plus 2 times the y to point E. Oh, that's my little one, sorry. Y to C plus 2ye is equal to a constant. Okay? Then over here, since little 2 has to be equal as well, we can say that the y to E plus the y to the weight also has to be a constant. Okay, now we don't need to bring these two equations together yet, but this y to the e and this ye is going to be the same, whatever it is. I mean, the elevator moves up and down, but that ye has to be equal to the same. All right, now the problem tells us some more information. The elevator E starts from rest. So that means that my velocity of E initial is equal to 0. And it moves upward with a constant acceleration. So the acceleration of E is a constant. These are all pieces of good news. If the counterweight W moves through 30 feet, so that means that Y of W is equal to 30 feet in 5 seconds. All right. What is the acceleration of the elevator and of the cable C? So we want to know the acceleration of the elevator equals what? And the acceleration of point C is equal to what? And we also want to know what is the velocity of the elevator at 5 seconds. Those are the 3 things that we want to know. All right, so the first thing is we know that because these are constants, we can also differentiate these equations and set them equal to 0. So we can say that the velocity of E plus the velocity of W is equal to 0. And we can say that the acceleration of E plus the acceleration of W is equal to 0. Over here, we can say that the velocity of C plus 2 times the velocity of E is equal to 0. And the acceleration of C plus 2 times the acceleration of E is equal to 0. All right, so we are told that the position of W moves downward. Is that correct? It says it moves through 30 feet, but I'm going to assume that it moves downward, right, in 5 seconds. Well, if the acceleration of E is a constant, that means that the acceleration of W is going to have to be a constant as well. It also means that the acceleration of C is going to have to be a constant. But that's kind of the first key piece of information. So if I take a look at the positions, the first thing I really think I would want to do is to develop an equation for what the acceleration or the velocity looks like for this particular item, just the weight itself. So we know that acceleration is constant. From our previous work, and this is also documented in the book, we know that x of w, and the other problem was x of b, at a constant acceleration with a 0 velocity is equal to a t squared over 2. Now, in order for this to be true, we know that the acceleration has to be a constant, and that the initial, I should call this y instead of x, since we're moving up and down, and that y, w initial, has to be equal to 0. So in other words, we're really talking about the displacement, which is the 30 feet. There it is. Okay. So I can plug that in and I can say 30 feet is equal to the acceleration of the weight times 5 seconds quantity squared divided by 2. Multiply up and I get 60 feet equals AW times 5 seconds squared. So I divide both sides. 25 seconds squared. And if I do that math, 25 goes into 62 times, with 10 left over, bring over another decimal place, 2.4 feet per second squared. All right. Now, I need to think a little bit about the direction. Okay? And the real idea is here, if W goes down, what's going to happen to E? Yes, E goes up. So if my acceleration, because there's really only one way for that to happen because we're not slowing down, that means if I call that A positive, that A up for E is going to be positive as well. But it'll come out in the math. I just kind of wanted to discuss that a little bit. So one of the questions it asks is, what is the acceleration of E? Well, I know that the acceleration of E plus the acceleration of W is equal to 0. I know then the acceleration of E equals minus the acceleration of W. So that means it's going to equal negative 2.4 feet per second squared, if I call this positive. Now, I'm not entirely sure. I would prefer to just use arrows because it can be a little strange from a physical point of view. I've defined this as being positive downward, so that means that this is negative going upward. But let's do it this way instead. Let's say A of the elevator is 2.4 feet per second squared up. Okay? And then that eliminates all details. All right. The next question is, what is the, well, we could do either, and let's go ahead and find out what's the acceleration of C. All right, let's think about that. If the elevator is going up, that means that this string is going up. Oops, sorry about that. And C has to be going down, doesn't it? In other words, the motor is spooling up that cable. All right, so, and you see, this is a really neat little engineering problem too, because we sort of do this combination where we look at the math, but then we also look at the picture and think about what those things mean. So it's not as formal in the mathematical sense as it would be for somebody like a physicist who would keep those signs a little bit, they would keep them in their head with a little bit more signage rather than the way that we're doing it, or the way that I'm doing it, and I'm making you follow along. So if you want to do it formally with math, as long as you indicate to me clearly, that's fine as well. So anyway, so we know that E is moving up, which means C is moving down. So if I look at the relationship between the acceleration of C and the acceleration of E, I see that the acceleration of C plus 2 times the acceleration of E is equal to 0. And I know that the acceleration of E is equal to 2.4 up. So A sub C is equal to negative 2 times 2.4 feet per second squared, or the acceleration of C is equal to negative 4.8 feet per second squared. But what that really means is a sub c equals 4.8 feet per second squared down. Like that. Okay? And then the last thing it asks me is, what is the velocity of the elevator after 5 seconds? Well, what do you think the relationship is between the velocity of the elevator and the velocity of the weight? Same, except one's up and one's down, right? All right. So, if we take a look at that, we can say that the velocity of the elevator plus the velocity of the weight is equal to 0. And we can also think about this constant acceleration thing, since we know the acceleration, well, we know the acceleration of c as well. But it's easier for me to see the acceleration of the weight. When I have that weight hanging out there, I just want to look at that. You know, that's like my thing. So let's go ahead and just do that. The acceleration of the weight then is, where did I put it? 2.4 feet per second squared, and that is going down. All right, so that means that, once again, the velocity is, if we look at that, we can say dv dt is equal to a, dv equals a dt, v2 minus v1 is equal to a times t2 minus t1. We're told that this is 5 seconds. We know that this is 2.4 feet per second squared. And we know that v1 is equal to 0 because we're told it starts at rest. Okay? So we basically get that the velocity 2, which is the velocity of the weight at 5 seconds, is equal to 2.4 feet per second times 5 seconds, which is 12 feet per second. Okay. And if the velocity of the weight is down, then I know that the velocity of the elevator is going to be equal to negative velocity of the weight. Velocity of the elevator equals the opposite of negative 12 feet per second down. So therefore, the velocity of the elevator at 5 seconds is equal to 12 feet per second up. Okay. All right. Do you guys have any questions about that? Excellent. All right. So, as I said before, we're going to skip section 11.3, and it's fairly interesting. But section 11.4, and we're going to do this very short, so you may want to read through this because there's a lot of information in section 11.4 that I'm not really going to introduce because we're going to work toward our end game, which is projectile motion. Okay, but basically 11.4 talks about curvilinear motion. And one of the things that we mean by, what we mean by curvilinear motion is something that doesn't necessarily move in a straight line. So if we have a particle that's moving in the xy plane, and it's moving along some sort of an arc, and it doesn't have to be a circular arc, just some sort of an arc, and it moves from point P to P prime. There are just a couple of definitions. One, the actual distance that it moves along the arc length is referred to as delta S. And the distance that it moves in a straight line between P and P prime is referred to as delta p, or just p minus delta p. And another way that we can think about it is the radius of that part, the distance between the origin and the particle, as changing from r to r prime. Okay? So those are just three geometric ways that we can look at this. But the truth of the matter is that as the limit of this delta s approaches 0, delta s, or delta p, approaches delta s, or vice versa. And so in the limit, the two equations become the same, and that is, of course, the derivative. Okay, now the reason that as engineers we're interested in curvilinear motion there are many at this point. But basically what we're aiming at in 11.4 is to examine projectile motion. And when we talk about projectile motion, what we're talking about is something that is not being acted on in the x direction by any external forces, but is being acted on in the y direction by gravity. And because x and y, I don't really know, I don't have any reason for having changed pen colors here, I just did. In the y direction, the acceleration would be, if we consider this to be positive up and negative down, 9.8 meters per second squared, or 32.2 feet per second squared. And in the x direction, the acceleration is equal to 0. What that really means for a projectile is if we fired something horizontally and we did not have gravity acting on it, and we didn't hit a wall, we continue going on and on forever. That's Newton's second law, that a particle that doesn't have a force acting on it will continue in a straight direction until a force acts on it. So in projectile motion, what happens is you throw something up in the air, or you shoot something up in the air. I was watching reruns of Game of Thrones last night, so I'm thinking about trebuchets and pots of boiling oil and all kinds of things like that. But basically, something that is being fired up in the air, if we didn't have gravity, would just keep moving in a straight direction. But at the end of the motion, something stops it. In this case, we have a wall that stops it, or if there isn't a wall, it's just going to hit the ground, and then the motion is going to stop. But what this does for us, because x and y are perpendicular to each other, we can separate out the motion. And most of 11.4 talks quite a bit about vector math. But basically, what we can say is the vector p, whatever you want to call that, the position vector, is basically going to be some component p of x in the I unit vector, dotted with the I unit vector. This represents the component of the position in the x direction, and some y component dotted with the j unit vector. So the unit vector here is called I, and the unit vector here is called j. Now there are other ways to write that. There are other forms of that equation. You can use, like, I think a lot of times in calculus, they'll just use components like this. Okay, this is just a different way of writing it. Now, that also means we know that velocity, and I am writing this as a vector now, I'm not talking about speed, is equal to basically dp dt. And because we have it broken down into these mutually orthogonal or perpendicular components, we could call this, if we're looking at the velocity, we could say this is dpx dti plus dpy dt j. And if we were talking about three-dimensional motion, we could just extend that into the z direction, call it k, dot it with the k unit vector. Now, there's another notation that we use sometimes for a derivative with respect to time. And I present this to you because it's in our textbook, and I don't want you to get confused about it. It's not a really commonly used mathematical notation. But we can say that the derivative of anything with respect to time, we might call, let's say, I'm going to give a component to simplify a little bit. We could call that p sub x with a dot over it. Have you guys seen this notation before? Okay. So I asked Martin Stenzing about it because I didn't feel like it was standard, and he agreed with me. I don't think he'd ever seen it before. So that's how odd it is. But it's commonly used in engineering applications. So if I were to rewrite this textbook, I might not use it at all, but since it's in your textbook, I want you to see it. Okay? So what that means is that instead of writing the velocity as dp dx dt dotted with the I unit vector, I could just say x p sub x dot I and p sub y dot j. So it simplifies it a little bit. Just for the record, this type of notation, the standard differential notation, is called Leibniz notation, and this is called Newtonian notation. Okay, so what this means for us then is that acceleration as a vector, we know, is going to be dv sub x dt dotted with the I direction, which we could just call v sub x dot I and v sub y dot j. Or we also know that that's the second derivative of position, which we write as two dots over the p sub x. So functionally, that changes absolutely nothing. It still means exactly the same thing. V sub x dot just means dvx dt, and double dot just means the second derivative of the component of position in the x direction with respect to time. So it means exactly the same thing, just a different way to look at it. All right. So what that leads us to is the idea of rectangular components of acceleration and velocity, which is what I've really just put down here. So we just got through a lot of vector stuff, and I kind of gave you the shortcut and the Cliff's Notes and the punchline. So that's really all that we really need for this piece of the puzzle, except to say that when we're talking about projectile motion, we don't talk about a function on a circle or a spiral or anything like that, because we know what the function looks like. We know that we have zero acceleration, constant velocity in the x direction, and we have a downward acceleration of gravity in the y direction. Changes a little bit, of course, if we get friction or air resistance, but in the simplest case, that's not a problem. All right, so when we do projectile motion, what we really need to do is to make sure that we separate out, we have this math, and this is really all the math that we're going to need, except for just understanding that acceleration, zero, constant. And then we have to draw a picture and decide where things are going to stop. Because if you try to analyze it only in the x direction, it will just go on forever and ever. And it's not true. It's going to stop when it hits the wall or when it hits the ground. So to kind of show you that idea, I wanted to do a problem 1189, which is a pretty good projectile motion problem. All right. So we have a guy standing here nicely on a field, broken out into the x and y coordinates. And I always call the stick figure who helps me. This is Ernie, the spokesmodel. So Ernie's going to help me by throwing a ball. And basically, he throws a ball with some velocity. And because of gravity in the y direction, it will reach some top of the arc, and then it will reach the ground before it stops moving. And the question says, a ball is thrown so that the motion is defined by these equations. X, in other words, its position here, is equal to 5 times t. And y is equal to 2 plus 6t minus 4.9 t squared, where x and y are measured in meters and t is measured in feet. Now these two things are going on at the same time until it stops moving. So there's doing this until it stops moving. So the limit is not set mathematically. The limit is set by the splat. Okay? Determine the velocity at t equals 1 second. And the velocity, remember, is a vector. So that's going to be dpx dt I plus dpy dt j. But I want that at 1 second. So I could say p sub x dot I plus p sub y dot j. A little bit easier notation. And then I want that at 1 second. And the horizontal distance that the ball travels before it hits the ground, which I would call x sub final. Right? All right. So here's my x. My p sub x dot then is just going to be the first derivative of that with respect to time. 5t differentiated is just 5, so it's 5i. P sub y, this differentiated 2 goes away. We have 6 minus 4.9 times 2, which is negative 9.8 t. So this is my velocity function. And it asks me what is the velocity at t equals 1 second. That's going to be 5i plus the quantity 6 minus 9.8 times 1, which is just 9.8 j. Or the velocity at t equals 1 is equal to 5i minus 3.8 j. And of course, that's in meters per second. Now, if we wanted to find the speed, we could do that. We could take this number and square it, this number square it, add them together, take the square root. And we could also find the direction because we have 5 in the x direction and negative 3.8 in the j direction. Now, the 5 in the x direction is going to remain constant, right? But the velocity in the y direction is going to change. It's going to be positive, it's going to be 0, it's going to be negative. All right? But that answers the question. So what's x sub final? Well, the real question is, if I just plugged it in here, it would depend on how much time there was. So what I need to do is to determine how much time there is using the y equation. And what's the kicker? What is the tie-in? Ha! Very good. So at t sub f, y equals 0 because it's going to hit the ground. It starts 2 meters up, so the guy's throwing it from 2 meters, just a little over 6 feet. But at the end, y is going to be equal to 0. So we get 0 is equal to 2 plus 6t minus 4.9t squared. And once again, this is a quadratic equation. This is a, this is b, and this is c. So I get negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. That's where the zeros are going to be of my equation. Oops. And I'm just going to finish this up. I've kept you guys too long, but we'll do it really quick. So we get negative 6 plus or minus the square root. 6 times 6 is 36. 8 times 4.9 is positive because I have 2 negative signs. is 39.2 all over 4. 39.2 plus 36 is 75. And if I take the square root of that, I get 8.67. So in other words, I get negative 6 plus or minus 8.67 all over 4. All right. We are talking about time. Yes, sir. Did I do arithmetic? Oh, gosh. Absolutely. What you said. Yeah. This is A. That's B, and this is C. All right. So then negative 6 plus or minus the square root of B squared minus 4 times A times C all over 2 times A. All right, and that actually changes everything because it's a minus down here, so that means we're going to have to take the minus root up here probably, right? I mean, in other words, we need to subtract that. So I get negative 6 plus or minus, I hope I'm doing this right. I may find that I have an arithmetic error, 8 plus or minus 8.67 all over negative 9.8, right? If I've got my signs correct. So what that means is this is negative. My numerator is going to have to be negative in order to get a positive time. So I take the value 8.67, add 6 to that. That would be a negative 14, divide it by 9.8, negative, and I get 1.5 seconds. All right, so that means it's going to travel for 1.5 seconds. So that means how far is it going to go? X final then is going to be 5 times 1.5, which is 7.5 meters. Right? Okay, so do you guys have any questions about that? And it's entirely possible I start going really quick and I get arithmetic mistakes. Yes?
So going back to where you but like right above your finger.
Yes.
You got the vector.
Yes.
You got the 5i plus 6 minus 9.18.
Yes.
So where did the 5i come from?
That's just right here. Yep. It just took the first derivative of that with respect to time. Yep. Good question. So you have a position, take the first derivative with respect to time, that's velocity. And that would be the velocity in the x direction,
So
or the x
just
component.
combine both of those together.
Exactly. Perfect. That is exactly. And you're using one to find out stuff about the other. Because like I said, if you plug in just t into x, you'll say, well, it's just going to go on forever. It's just going to levitate above the ground, and you'll never, but yeah, but that's not physically what's going to happen. So, excellent question. All right, do you guys have any other questions for me? All right, then. That is our long lecture for the day. And you now have enough material to do the first 2 pieces of the homework. And if you look at the podium PC, let me switch this down, you'll see that we have one more lecture. And then we'll have one more lecture on Wednesday, and then the homework will actually be due Friday. So it doesn't have to come in this class. You can come to class on Friday and ask me questions, and then submit it through Moodle before 5 minutes to midnight that night. All right? All right. Thank you guys for your attention, and I will look forward to seeing you on Wednesday.